It's getting grippy. It's like 10 o'clock. It's too early in the morning or something. Did I tell you about my first semester in college? No. So my first semester, I was, this bright-eyed, excited international student, so happy to be in a country where I could take whatever courses I wanted, like freedom. So I just said, I'm going to take exactly the courses that I wanted, and it turned out that meant I had a class every day, Monday through Friday at 8 a.m. And it was fine. I went to all of my classes, but I said, that freedom thing cuts both ways. So my second semester, I was absolutely certain, I totally made sure that the earliest class I had was 1 o'clock. Didn't make every start of class either, I must confess. So it's, yeah. So anyway, this class is at 10 o'clock. It turns out, by the way, my class that starts at 11 o'clock, the next hour, I've gotten lots of complaints that apparently it's too early in the day. So, yeah. Anyway, welcome to computer science. So, we're going to continue with graphs. I would like, as a starting exercise, so we want to write this function. We're given a graph. We're given two keys in the graph. Okay? And what we want to determine is whether we can get from this key to this key. Okay? That's our Boolean answer. And the main helper you're going to need is, what do you think the contract of neighbors is going to be? Contract of neighbors. Talk to your neighbor and tell me what the contract of neighbors is going to be. Contract of neighbors. Contract of neighbors. Proposals? Proposals? Anyone with a proposal? Their proposal?
Key, comma, graph produces list of key.
Key, comma, graph produces a list of key. Right? Takes a key and tell me which graph it is in, right? And then gets back a list of keys. These are pretty general interfaces, right? Depending on the particular way you defined your graph, you may not need to. For example, if we actually had graphs with true cycles in them, we don't need to also pass the graph, and this is a very general interface that accommodates all the different graph definitions that we've seen. Okay? So, given a key and a graph gives me back a list of keys. All right? Okay. So, using this, write this. Go. I'll give you about 5 minutes. Write code, write code.
This is probably a good place to start. First, we need. Well, this is N1 or J1. Right. G. First things first, grab the neighbors in front of the list. Yeah, but then this is the first step. We just have to be like, we're going to want to help with this function, which also takes in.
That's like your base. And then you fall.
Yeah. So I think we want to help her with like a
But I don't think that there's
version of the function, which also takes in
what's the what do you want
Manages.
Oh, what's the
like K1 K2 equals like how do we?
Okay, so if neighbors of P1 dot member.
I want to pen first.
So,
Oh wait, we don't actually be able to fill.
not do that.
I just think
Because you want to make sure.
Then here, all we do is read.
I mean
So we have to
Yeah, we will.
So here,
You mean do it
neighbors, check it for each of the neighbors. If it's first checked,
I was just practice. For all the tracks, how you can do set operations?
so
we could use this.
You're gonna use what, 70 whatever set list operations are in.
It's like basically remove all the ones that are easily considered the ones that are not.
I was gonna do it.
I'll do filter.
Filter's probably the easiest. So that's not which is first not filtered.
X number of
so really
lambda, like that number is offset.
Meter.
and then this is
What would be the set membership is cheap. So will neighbors return all the neighbors, or can we like make it so that it returns?
No, it's gonna return all the neighbors, right? The graph doesn't know anything about them. It's completely agnostic to the code you're writing.
Alright, so new equals that. Then,
No, you need to check if you're mutually dependent.
so first you can do.
So I would check through. Oh,
Well, but first you just need to check like if.
oh it's not
because we'll do that in for each element. We'll check if it's K2.
it's like
But then we're going to be doing a demo. It might be easier to search all of the neighbors.
Or actually, it might be easier to check out the top say is K1 equal to.
But then what if because then if you're checking before you filter, you'll like check, you'll go to that.
That one thing, you could also just pass it as a list of the selection. And I think that would be easier because then the fold can just call us. You don't have to do any checking. Yeah, so if you say if K1 equals K2.
This is already the fifth. K1 not equal. So this would be a list.
And then now all we need to do is fold and call each scene.
Or no. This is
the notice of both any of those.
like, yeah, there's no reason for us not to do it yet, because then when we're calling it subsequently, we're going to still do it. No, the adding.
If you do 2, it would have to be 3, 4, 5. It just gives you all these things.
Oh, and if we're using a
It
second
would be fold,
well, if we're just using, it depends on how they're native and defined. You can just do K1 plus.
We're doing a general thing.
Or it's S plus neighbors, sorry.
Oh, it's actually this.
Yeah, we haven't actually checked. Because it does. We haven't actually looked to see if any of them are the thing.
You're right. You gotta
Alright, so I think we take this one out now. Since we're doing a split, now we'll fold over the or no, we'll fold over. Do we need it?
Okay, I'm going to bring you back for just a moment. So it looks like people are hard at work, and this is great. Just take a quick voice vote. How many people would like a little more time? Okay, keep going.
So we could just create a big list of A and all of our neighbors, and then check if it's in there.
Just want to look at the rest.
if you're all of the same.
Yeah, because that'll be handled by just doing a link of one.
And this on the next episode.
And then we do this after.
And then here, this is like
This is to give a note. You do all the notes.
is F equal to K1.
Or we need
Whether we want to check if you look at I would Paul's scene.
we need to form a
So we need to if the one that you need isn't there. If not, then you have to pull through, then you have to filter, then each time you have to get back to the new scene.
Yes.
Maybe that should return.
Oh, right.
It doesn't. The tuple of scene is
I mean, you can write whatever you want.
If you've seen node 2, you don't have to look at 1, 4, 5, and 3. It's already set to you.
What's going to happen is let's say you were 1 to 2, 5, 5 to 2. But when you look at 2, the way I would write it, yeah. That makes
Yeah. If you check if it's in any of the neighbors, if you check if it's in the list, because you're not preparing.
Because you would stop if it's
Yeah. If you're doing depth first, like if you were at 2, you check 3, 6, 7, 4 instead of 3, 4, 5.
That first check
It follows the path until the end. So remember to
You go to the next one.
now you have to go and not
because like you're gonna like check everything out there, but then you're gonna check everything that way, then you're gonna only go down to one node and then you're gonna go back up and then like they're checking the layer.
No, you need to check down.
So it's like
Like, not here, we have to read this.
That's like your depth is the distance from your vision. Yeah, so your depth is your and then your breadth. That's the same thing as that go straight down.
And then there's
Say that it's no, that it's not in the tree or in the graph.
gotta call Rich up.
And then the first thing we should do is we should order lean in that. Yeah, that's why I'm getting this thing. Well, but the nice thing about that was that definitely not your once you get back to I mean,
All right, your attention again. Everyone back. So another quick voice vote. Who needs more time? Less. Okay, I'll give you 30 seconds to wrap up. Go.
This is like the 5 doesn't have any neighbors. So base dot
so this would need to be
All right, in 5, 4, 3, 2, 1. We're back. Okay. All right. Sounds like I see a few, or hear a few different variations on this. How about we do this? Why don't we start? Why don't we start in the middle this time? Okay. So your group or individual, whatever. So what was the general structure of your solution? Did you define any additional functions? Shh, everyone,
Yes.
please. Yeah. What did you define?
Key, which would just return the key.
Folks. Shh. Key that would what? Return?
The key of an element in the graph.
How do you ask the graph for an element? You have to give it a key, right?
I think I'm using the wrong data structure.
Yeah, okay. Because remember, graphs have a key, and given a key, they're going to give you back the corresponding element. So, okay, so that could be the identity function. Good. Okay, so there's nothing wrong with that. Okay, so given that, what else did you have to define?
That was the last.
That was the only thing you defined. So everything else was done in terms of reach. Okay, good. Let's do this at a high level. Did anyone define any other functions? Find it useful to define any other functions? Back there, yeah.
I don't know, I thought it was nice to have a reach helper function that could take like a list of keys or what's already been traversed.
Okay, so it took, so give me the full signature.
Like a traverse, which is like
A list of key, okay?
Like what you're visiting, so which is another list of key.
What you're visiting, which is a list of
So
keys.
like, just the like lace from a particular key.
Okay,
And then that actually the target key. And would produce a boolean.
okay. So this is the target,
Yeah.
this is the scene list, and what's this?
This is
The visiting, the ones you're visiting.
Yeah, the links from a particular.
Okay, good. Okay, other helpers, anybody else have a different helper structure?
we had the same thing except that
Just give me the whole signature.
list of keys, key, graph, returns a pair of values, so returns a Boolean and a.
We'll get to, let's just stick with Boolean for now, and then we'll get more complicated as needed, okay? So what is this list of keys?
Yeah, it's the C.
It's a scene list, okay. And then this is the same as that, presumably, and that's the same as that,
Yep.
and that's the same as that. Okay, good. Any others? Yeah, back there.
Yeah, list of key,
Uh-huh,
and then key,
uh-huh,
and then graph,
uh-huh.
and return list of key.
Okay, we'll get back to the return type in a moment, okay. Okay, so what is this? What is this list of key?
Scene,
It's the scene, okay, so it's the same as scene. What's this key?
the current node.
The current node, okay. So we have a current, target, and the graph is obviously the graph. Okay, and so this is the target or the current node?
The current one.
Current one, okay, so this is this thing over here, and then you have the graph and some return type. Okay, anybody else have, yeah?
We made a remove function which takes a key and a graph and returns a graph.
Remove takes a key and a graph and returns a graph. Okay. Any others? Okay. So tell you what. Okay, folks. Shh. Let's pay attention here. Let's see. I've got. Let's focus on the left-hand side of the argument list for now. Okay. So we have 1, 2, 3, 4 different functions here. Anybody want to argue in favor or against any of these? I mean, you can't argue against reach. That's the interface I want you to implement. So that one's a given. How many of you are satisfied with only a reach function? And having no other helper functions, none of these helper functions. Vote yes if you're happy with none of these helper functions you think these helper functions are unnecessary. Yes? Vote No? Ooh, pretty strong. Why not? Why are you unhappy with it? Why are you unhappy with there being no helper functions? Yeah.
Well, it seems like you have to keep track of the nodes.
Got to keep track of what you've seen. If you don't keep track of what you've seen, you cycles, right? It's the DAG problem, but much worse. You have to keep track of what you've seen. So you need some kind of helper function to keep track of what you've seen. Okay? Now we have a choice of all these different helper functions. We have 1, 2, 3 different helper function interfaces here. So I will allow multiple voting. You can like more than one thing here, right? So how many of you like this one? How many of you like this? How many of you like this? Ooh. Okay, why is this one unpopular? Yeah.
If I don't have the target, I don't really know when to terminate.
If I don't have the target, I don't know when to terminate. Can somebody defend this? I mean, it seems weird, right? I have what I've seen. I have where I am. Without a target, like how am I supposed to know when to terminate? Yeah.
Target might be C.
It depends on where this function is located. If the helper function is at the top level, clearly it has no way of terminating. If the helper function is inside reach, right? What is the parameter? What is the one parameter? Well, there's sort of 2 parameters of reach actually that never change. Target and graph. So I would argue I'm not happy about this one because if you're going to remove the target, you should also remove graph. Because neither one changes. Okay? They're both immutable. Now I understand that you propose this and you also have a remove function, which I'm still a little dubious about. We'll get to that. Maybe we need it, maybe we don't. But certainly, this is a very reasonable interface, right? Where are we currently traversing? What have we seen so far? The target is not going to change, and the graph is not going to change. Okay? Of course, if you have a remove function, then you probably want the graph to also be a parameter. Yeah?
If this is inside reach, then why do you need to pass in the current key as well? If you see that inside the scope of reach as well?
Ah, Duke, here's a great question. If we put reach helper inside reach, why do we need this key as a parameter at all. Why do we need it? Do we need it? Do we need it? How many of you think yes and how many of you think no? How many votes for yes? How many votes for no? There's got to be somebody voting for no. We're going to be talking about the question. Why do we need it?
Because it changes what our current node is.
Because our traversal is going to keep changing what our current node is. Okay? We're going to keep moving around the graph relative to the graph being unfixed and relative to our target being fixed. So if this is my graph and this is my target, I'm trying this node, I'm trying this node, I'm trying this node, I'm trying various other nodes in the tree, in the graph, before I get to my target or say I've run out of nodes. Okay? So far so good? Okay, good. Remove. Do we need remove? Do we not need to remove? Yeah.
For the implementation that we did, yes.
Okay.
Because we don't have a helper function, we literally just keep track of
Here's an interesting strategy. So maybe you don't, there's a different way to do it entirely where you keep like breaking up your graph, right? So remember, you need the scene list to make sure that you don't go in a loop. Another way to do it is to just pretend that that node that you visited is gone from the graph entirely. Yeah.
Wouldn't that remove edges? Like,
Would that remove edges? Would that? Yeah.
But it probably only remove edges that you've already traversed. Because if you're removing
Yeah,
those.
so it's going to remove. So here's the thing. If I go here and let's say I visit 2. And so what I'm going to do is I'm going to remove 2 when I do the recursive call. Okay? What I have to do is I have to keep track of the fact that 4, 5, and 3 also exist. Okay? Now, you might say, well, what if 3 points back to 2? Well, but that's the edge I don't want to take because I've seen 2 already, right? So I don't want to go back to 2 because I've already seen it. And therefore, I can just make sort of quote-unquote forward progress. Actually, I like having this edge here. Let me keep this edge here. I want to keep making forward progress. And so 2's, I've already accounted for 2 by the fact that I've gone to its forward neighbors. I don't need to go back to 2. So that's like a good kind of deletion, basically. Okay? So you could think of it that way. I'm going to prefer to not think of it that way. I think it's a very complicated way of thinking about it. Also because when you deal with large graphs, you don't want to go about destroying part of the graph. It's hard, it's complicated, it's expensive to delete part of the graph. And it's actually worse than that. If you work at a company where there's graphs like a part of your central data structure, right? And we know of several companies we've now talked about where the graph is a central data structure, like Facebook or Google or whatever. First of all, the graph is ginormous, and secondly, you don't get to make a local copy of it and start deleting people from the social graph and things like that, right? At least you're not supposed to, I suppose. So what happens is you have some internal data structures. You have an external fixed data structure that's like company-wide. You have an internal data structure that's tracking your particular computation. There could be thousands of people running thousands of jobs over that data structure. You think of the data structure as a fixed, immutable thing, and your computation just has its own local data structures to keep track of that. So keeping track of a scene list is a much more accurate way to think about how you would process that kind of graph. Okay? So for this course, this semester, for the homeworks you're going to do, I'm going to ask you to not think about updating the graph. I'm going to ask you to think about the graph as being an inviolate thing, and you keep some auxiliary data structure to keep track of your traversals. Does that make sense? We're good with that? Okay. And are you okay with that being an equivalent strategy? Okay, great. Okay, so now let me show you a piece of code. Is this stuff on? You see anything? Yeah. It's supposed to come on there too. Oh, okay. System preferences. Oh, I know. I turned mirroring off. That's right. Oh yeah, that's an interesting piece of code, isn't it? It's like pirate inside Dr. Racket. Yeah, what's up with that? Very interesting. Okay. Okay, so here's what I'm going to give you, okay? I have, okay, look at it on the boards, okay? Look at it, no, I don't want to erase everything. So I've got a function reach, okay? And what reach has, it has a reach helper. It's got a source and a destination. So our outer reach has a source and destination in a graph. Our reach helper also takes a source and destination and a visited list.
Okay? Maybe not all of those parameters are necessary. If the visited list, if the source is a member of the visited list, that means we've hit a cycle at that point. Okay, and we haven't yet finished. So that means we return false. Otherwise, if the source and destination are the same, then we return true, right? Because we've finally gotten to the point we're trying to get to. Otherwise, we make a new visited list by linking the source onto the visited list. And then we map over all of the neighbors and check whether we get to the thing or not recursively. Okay? And we start off with the empty list of visited nodes. Okay. So, what I want you to do now is talk to your neighbors and critique this code. Don't critique the name choices, okay? Critique the code in terms of its potential correctness or incorrectness. Go.
They're returning booleans.
So OR map basically iterates. Focus. OR map iterates over all the neighbors, and it's basically OR of the first thing, of the second thing, of the second thing. It's like it's splicing an OR into a list of results. Okay, and so it also terminates if it sees one, it stops before it goes on to the rest, exactly as you'd expect OR to do. Okay, it actually slightly doesn't quite, but pretend it does. It won't matter here. Okay, yeah.
Do you care if you said worthless class consequences? If the code is more efficient, stylistically and but not the best.
I care about both.
The only thing we care about is just like so then
I'm wondering if one of them wants to help or not. Let's first make sure we get based on
Correct or not.
It's never going to be cycle because
You don't care about
you'll read it from you're not counting that technically the same.
Just pretend OR map. It's just OR map. Okay? It's just a higher order function.
Can't say how bad.
It's just like that's another way to do it.
Yeah, that's or like, can you like I mean, you say if if not visited that member SRC and or SRC then
Okay. In 5, 4, 3, 2, 1, and we're back. All right. Comments? Anyone? Like, oh, I would assume there are going to be a lot of hands going up. Yes.
I think I may have found like a counterexample.
Like a bug? Okay, hold on to that. Any other comments? Any comments? Yeah.
I think it's correct, but it might like have a few more recursive calls than necessary.
More calls than necessary. So somebody was asking, like, how do we care about like performance versus correctness? Get it right first, and then we'll worry about performance, right? Because if you don't care about correctness, I can give you very efficient solutions, right? So, like, false, true. Take your pick. Constant time, always easy. Yeah.
It also violates the style guide, like returning booleans or if statements.
Actually, in this case, it's not really. There's not much of a choice here, right? Because it's not if something is false, else something true. There's also another else clause, right? So you could write this with a much more complicated Boolean expression with nots, but I think it would actually not be as clear, right? So this is not exactly a violation. Yeah.
Why not use an ask?
Sorry?
Why not use an ask?
We could use an ask instead. At this point in the book, I hadn't introduced ask. Okay. Other questions? Other comments? Other comments? Comments? We're good? Okay. So let's talk about correctness now. Everyone, let's focus here. Let's talk about correctness. Correctness. How many of you, we're going to do a straight up vote, correct, not correct. How many of you think it's correct? Great. How many of you think it's not correct? Ooh. Okay. Tell you what. Can you give me a counter example? It sounds like you have a counter example. What's your counter example?
Like, you have like,
Well, I can come over and take a look if you don't mind. Just a basic cycle. So how about that cycle over there? The 2-3 cycle we have there.
yeah,
So where would we have to start? Where would we have to finish to discover the problem?
like in this.
Actually, I mean, how about I just copy your example down?
Yeah.
So what was it? It's
One, yeah, two,
like that?
yeah, and then from that one there's one.
Okay, and let's just, I don't want to use 1, 2, 3, I'll use A, B, C instead, okay? Okay, so where are we starting from?
So from like A to D.
Well, which node are we trying to find? D. Start from, source is A, source is A, destination is D. So we want to know, can we find a path from A to D? First of all, what's the correct answer? Yes, we can find a path from A to D. So what happens over here? Let me scroll this up a little bit maybe. Okay. Well, I'll let you look at the sides if you can't read the code here. So what happens? We're starting from A and we're trying to get to D. And so we're going to call reacher on A to D with what is the visited list? Empty. Okay. So is it a member? Well, no, it's not. Okay. So is it equal? No, it's not. So now we have to look at new visited. New visitors, we're going to link A onto the visited list. Okay? So visited is initially empty, and now it's the list containing A, right? And then we're going to look at all of the neighbors, where we're going to go look at B with the visited being A, right? What happens when we visit B with the visited being A? So we're now going to call reacher again.
It's not visited.
Right? So now we're going to call reacher on B, still looking for D, with the neighbor being, with now the visited list being A. Right? Okay. So now we're going to do the OR map again. So now we're going to say, well, it's not visited and it's not equal. So now we're going to call, so let's see, source, destination. So initially we had A, D with the empty list. Now we're going to call BD with visited A. Now we're going to call CD with, we're going to link B onto the list, so now we get A.
It is not.
Okay. Sorry?
No.
So far so good? Okay. And now we're going to call this on neighbors, which is A and D. Okay? So we're going to call it on A and D. So now our source is going to be A, destination is going to be D, and we're going to be, well, it's not the top line.
Well, you need to move new.
We have a new visited list. Right? Yes? Okay. No,
wait, never mind.
If you say no, then is this the correct next call?
Yes.
Who thinks it's not the correct next call? If it's not, tell me why not. Okay, good. I've intimidated you into silence. Good. Okay, what happens when we come here? Is A a member visited? Yes. So it's going to return false. Okay? Good? So we'll return false. And now we come back, and we're now going to go to the next neighbor. C has another neighbor, D. Right? And so we're going to call D, CBA, and that's going to return true. And now we're going to get a true back, and now it's an OR map, so trues are going to percolate up. So, is this a counterexample? Yeah.
Why does it go to A before D?
It's going to the list of neighbors, right? So it depends on how I wrote the neighbors down. Right? I could have written the neighbors in the list structure. I could have written as DA or AD. You can think of it as a set, in which case the order is independent, but it's still going to visit something. Okay? So I said, let's assume it visits A first just to see if that breaks anything. And if it doesn't, great. If it does, that will be a problem because we might end up visiting that order.
Can we assume OR map returns false on empty list because if not, it gives some false.
Well, OR map has to return the right default on the empty list,
Okay.
which has to be the identity for OR, which has to be false, right? It's a 0. The identity for AND is 1, the identity for OR is 0. So AND map would return true, OR map returns false. So we're good? Is this code correct? Yeah?
I think if you had something like 2 loops almost, because it's not like updating in the OR map part, it's not updating the new visited with the stuff. With the new, with the stuff it's visited in now.
Yeah? What? You think it works?
No.
You're okay with it? You're okay with it? Are you okay with it?
Yeah, I feel like for any cycle, it's going to terminate. So then if 2 cycles are made up of, or if a figure eight is made up of 2 cycles, then each of the cycles is going to terminate separately.
Okay, there's an argument, okay?
I think it only terminates once it's found the thing because of the OR map. So if it's supposed to return false, it'll go into an infinite loop.
That's a possibility.
I think that any call is gonna terminate in at least the number, like however many nodes you have in the graph, number of.
So let's first figure out termination, right? That's the critical question of graph. Let's not even worry about how many traversals or anything. Let's figure out whether this program always correctly terminates. It's all easy to write an incorrectly terminating program, right? Does it correctly terminate? Yeah.
It does correctly terminate because on a cycle, there will be a path. Our path will start from the source and get back to a point that was on the point, like on our path so far. So that would be a cycle. If it ever does that, it will terminate. If it doesn't have a cycle in the graph anywhere, then it will reach the end at some point. It just might double up on it, so it will always reach an end.
It's a possibility. Yeah.
It's not going to terminate because if you read the exercise, it says that there's a problem. I don't know what the problem is.
Now, yeah, we don't know what the problem is, and keep in mind the exercises are meant to make you think, so the exercises aren't always guaranteed to be right. So good try, good try, good try, good try, good try. Yeah. A single node. Oh, how about a single node? Sure. So you want me to have like let me call it alpha. Okay, so okay, like that.
Yeah.
Okay. So what happens here?
Terminates.
Yeah, we'll say.
Let's say we start with source is alpha, destination is beta. It's a node that's not reachable. Okay? Visited list is empty. Well, we're going to add alpha to the visited list and recur on all of its neighbors, which is alpha. So I think that terminates. I think that one's okay. What if what? Sorry? So, sure. Hey, one at a time. One at a time. Wait, somebody's talking. Hello, everyone. Please. Yeah.
What if the node doesn't refer to itself?
Okay. So let's try that. Sure. So what's your graph?
Just the node itself.
Alpha and beta. This is my entire graph. Okay. And I'm asking for paths. Does alpha get to beta? Okay. So what happens here? We're gonna add alpha to the source. All of its neighbors have to get traversed. So beta is our target. What are all of alpha's neighbors? Empty. So neighbors is going to be empty. So we're going to do an OR map over the empty list, which means we have nothing to OR together, which means we're going to get the base answer. The base answer is going to be false. And then I think we terminate, right? Yeah. And we're going to get the answer false. Is that the right answer?
Yep.
Yes, it is. Okay, good. Okay.
What if you had an example where your key, like your source was alpha and then your target was also alpha, but in that case, alpha is not referring to itself?
Well, there can be only one node of a given key in a graph. Right? Remember, otherwise all of our graphs are broken. So that's the notion of a key, is it's like a unique identifier and there's only one thing that matches that identifier. It's also unforgeable if you want to talk about the security implications, right? So I can't have two different nodes named alpha, then they're not keys anymore. Okay? So clever, but not outside the rules a little bit. Yeah?
I might not be understanding you visited well, Oh, but if you had something that was kind of like a tree, but at the end it connects.
Ooh, okay, so kind of like a tree, but at the end it does some connecting. So we have something that's kind of like a tree. And then somewhere down here there's some monkey business, right? Something connects to something over here.
So what's on the left side doesn't know what's on the right side?
Yeah.
So like if you start cycling up the right, like it has never seen that, but it has seen it.
Yeah. So what if, so give me an edge. Somebody see if you can build on this. Can you give me an edge? I've got, I'm running out of alphabet now. I mean, Hindi alphabet, anyone okay with that? Do we have any other alphabet systems in common?
I mean, tally.
Huh? Italics? Okay, I can do italics. I
I was saying tally.
You want me to use different typefaces? Is that what's going on? Okay. So, where do you want an edge from where to where? Next, I'll be like, I'm a Garamond purist here or something. Okay. So, where do you want an edge from where to where? To make this example be a counterexample. Yeah.
Something like E to F and F to C or C to
E to F and F to C, something like that.
Something, yeah. Well, I don't know what the destination though is. If it's C, then it's true.
Oh wait, no.
If it's like,
Okay, here's what I'm going to do. This is too much fun. I'm going to let you go home and think about this. Okay? This is way too much fun for me now. So, we've seen one thing that doesn't work. We've seen another thing that doesn't work, a third thing that doesn't work, and now we're on to our fourth example. And there's something about like cross edges and tree-like things and what if, by the way, there was an edge in the other direction? Okay, go. I want definitive answers on Friday. Okay, so what? Give me a definitive answer. Okay, fine, you get an extension till Monday then.